Alright, so today we're diving deep into the world of spectroscopy. This is a powerful analytical tool used in chemistry to determine the structure and composition of molecules. We'll be covering three major types of spectroscopy in detail: infrared, IR, spectroscopy, ultraviolet-visible, UVVis spectroscopy, and nuclear magnetic resonance, NMR spectroscopy. Whether you're a student prepping for a big exam, or just curious about how scientists analyze molecular structures, this video has got you covered. Let's get started. Spectroscopy is a technique that involves studying how light interacts with matter to gain insights into molecular structure. Most of the methods we'll discuss today are examples of absorption spectroscopy. In absorption spectroscopy, when a molecule is exposed to light, it may absorb a photon if the photon's energy matches the gap between two specific energy levels of the molecule. This transition pushes the molecule from its ground state to an excited state. Molecules prefer to be in their ground state, so after absorbing energy, they tend to return to this lower energy state by releasing energy. This release can be in the form of heat or light. By measuring the energy absorbed and released, we can infer details about the molecule's structure. Different types of light, such as infrared, ultraviolet, and visible, cause different transitions in molecules, allowing us to gather various structural information. Let's kick things off with mass spectrometry. Unlike absorption spectroscopy, mass spectrometry doesn't involve light absorption, but is crucial for determining the mass of compounds in a sample. In a mass spectrometer, molecules are ionized, usually by bombarding them with high-energy electrons. These ions are then passed through a magnetic field, which deflects their path based on their mass-to-charge ratio, or m/e. The result is a mass spectrum, which shows peaks corresponding to the molecular ions and fragments. Peaks above the molecular weight indicate isotopic variance, while those below represent molecular fragments. For example, in a mass spectrum of N-non-ane, which has a molecular weight of 128 grams per mole, peaks at lower masses indicate fragments formed by breaking the molecule into smaller parts. Additionally, the presence of specific isotopes like bromine and chlorine, which have characteristic natural abundances, can help identify elements in the molecule. Moving on to UVVis spectroscopy, which is a type of absorption spectroscopy. UVVis focuses on the ultraviolet and visible parts of the electromagnetic spectrum. It's especially useful for studying conjugated systems in organic molecules and transition metal complexes. UVVis spectroscopy measures electronic transitions where electrons are excited from ground state to higher energy states. The wavelength of maximum absorption, or lambda max, tells us about the extent of conjugation in a molecule. The more extensive the conjugation, the longer the wavelength of maximum absorption. For example, polycyclic aromatic hydrocarbons like anthracene, tetracene, and pentacene exhibit increasing lambda max with each additional aromatic ring reflecting the growth in their conjugated systems. Moreover, the color a compound appears is the complement of the color it absorbs. A compound absorbing in the blue region will appear orange, as these are complementary colors. Understanding these principles can help in identifying compounds based on their UV-Vis spectra. Now, let's delve into infrared, IR spectroscopy. IR spectroscopy is another form of absorption spectroscopy, but focuses on molecular vibrations. When molecules absorb IR radiation, their bonds vibrate, stretch, or bend at specific frequencies. These frequencies correspond to the wave numbers in the IR spectrum, usually ranging from 4,000 to 400 wave numbers. The IR spectrum provides a wealth of information. For instance, a carbonyl, or C=O, group has a strong, sharp absorption around 1700 wave numbers, while an OH stretch appears as a broad peak around 3200 to 3600 wave numbers. Recognizing these characteristic peaks helps identify functional groups in organic molecules. Additionally, CH stretches are seen in the range 2850 to 3300 wave numbers, depending on whether the carbon is sp, sp2, or sp3 hybridized. For the MCAT, it's crucial to memorize key IR absorptions. Carbonyl, C=O, around 1700 wave numbers, strong and sharp. Carbon double bond carbon, C=C, around 1650 wave numbers, variable. Carbon triple bond carbon, C triple bond C, 2100 to 2260 wave numbers, variable. OH, 3200 to 3650 wave numbers, broad and strong. These values will help you quickly identify common functional groups. Finally, we have 1H nuclear magnetic resonance, NMR spectroscopy, a technique that uses radiofrequency radiation to probe the environment around hydrogen atoms in a molecule. In NMR, the nuclei of hydrogen atoms align in a strong magnetic field. When exposed to specific radio frequencies, they absorb energy and flip their spin states, which is detected and displayed as an NMR spectrum. The NMR spectrum provides 4 critical pieces of information. 1. Number of signals indicates the number of chemically non-equivalent hydrogen environments. 2. Splitting patterns shows how many neighboring hydrogens are adjacent to each set, following the n+1 rule. Integration, proportional to the number of protons in each environment, shown as the area under each peak. 4. Chemical shifts provide insights into the electronic environment around the hydrogens, with more d-shielded protons appearing downfield to the left, and shielded protons upfield to the right. Let's look at some examples. A methyl group, CH3, typically appears as a singlet because all 3 hydrogens are equivalent. An ethyl group, CH2CH3, has 2 distinct environments. The CH2 hydrogens appear as a quartet due to 3 adjacent hydrogens, and the CH3 hydrogens appear as a triplet due to 2 adjacent hydrogens. Recognizing these patterns is key for interpreting NMR spectra. Also remember common chemical shifts for different functional groups. Aldehydes, 9 to 10 ppm. Aromatic protons, 6.5 to 8 ppm. Alkenes, 5 to 6 ppm. Alcohols, 2 to 5 ppm. Variable due to hydrogen bonding. These shifts will help you deduce the structure of organic molecules from NMR data. Alright, so there you have it. We've covered the essentials of IR, UVVis, and NMR spectroscopy. These techniques are powerful tools for understanding molecular structures, and are widely used in both academic research and practical applications like medicine and environmental science. By mastering these principles, you're well on your way to becoming proficient in organic chemistry and spectroscopy. If you enjoyed this video, please give it a thumbs up, share it with your friends, and subscribe for more insightful chemistry content. And if you're using the King of the Curve app or web app, don't forget to check out the spectroscopy resources we have there. The app has interactive quizzes and detailed study materials to help you ace your exams. Leave a like and comment on what topics you'd like to see next, and explore the app for even more detailed content. Thanks for watching, and good luck studying.